So welcome everybody, thank you for coming. Today's speaker is Professor Bonilla from University in Madrid. So for me it's really a pleasure to have him here, first for personal reasons. Quite a few of my publications with my PhD work and in collaboration with him. And second, of course, because he's a very well-known researcher in this field of non-linear transport and applied mathematics. In fact, he's a full professor in his University in Madrid in applied mathematics. And before that, he had permanent positions in Barcelona and Sistemas. He has been a visiting professor in many universities, in Stanford and also Harvard. And if my rapid search is not wrong, I think he has published more than 200 publications and received 3,000 citations. Just to give you some idea of his scientific career. Anyway, today he's going to talk about graphene, okay, which is very popular material.
Thank you very much. It's a pleasure for me to be here, and I would like to start by thanking the organizers, and particularly Bonilla, Rosa, and Lorenz for the invitation. So today I'm going to talk about some work that we have done in the last few years about the mechanics properties of graphene. So not so much about electronics and so on, but mechanical properties. This work has been done in collaboration with Ana Carpio, so all of it, and parts of it have been done in collaboration with Fernando de Juan María Posmediano is the Instituto for Material Science of Madrid, Antonio Prados, Universidad de Sevilla, Rubén Rosales at the MIT, and Jamie Warner, who is an experimentalist at the University of Oxford. Okay, so this is the outline of the talk. I'll be giving a general introduction, and I'll keep some of the stuff at a pretty basic level, as I was told before. Can't do that. So we'll see how, based upon experimental results, you can consider defects in the graphene lattice as the cause of dislocations. And by just using ideas from elasticity and simple models, you can predict a lot of things, like for instance, which defects are going to be stable of this sort. And in recent experiments at Oxford, people looked more carefully into this, and they were able to map experimentally the strain or rotation fields about defects. We see that we also have some theory that explains this data and has some surprising elements a posteriori. I think another problem that is of current interest is that when people first looked into graphene, the TM, they observed that the sheets of suspended graphene sheets were covered with ripples. And there are many theories about why these ripples happen and how they evolve, and I'll show you what we try to do to understand the dynamics of these ripples with very simple statistical mechanics models. Then have these soft springs and whatnot that we do from experimental data in totally different area, like graphene resonators. I think I'll end up with some conclusions. Okay, so let me start by just reminding you that graphene is just a monolayer of carbon atoms that are arranged in a honeycomb lattice. And graphite, which is a well-known material, is just a stack of graphene sheets, just molded together by weak van der Waals forces. It's well known that the first experiments that attracted attention to the exotic properties of electric field in graphene are due to Novoselov, Gaim, and co-workers. And in 2004, and they were awarded the 2010 Nobel Prize in Physics for that work. Among different properties of graphene are that the charge carriers, as you know, are massless Dirac fermions. So the certain relation, the relation between the energy and the wave vector is linear, as in the case of photons, of course, with the Fermi velocity instead of the speed of light. And this changes a lot of things. In particular, you can use a lot of the 2D electrodynamics to understand this material. That's very exciting, and tons of papers have been written about that. About measurements, graphene has enormous electron mobility, also great thermal conductivity, has anomalous quantum Hall effect. It's ballistic, so it means that before these electrons collide with something, they just run for just below a micron, which is a huge mean-free path. Then the other thing is that just by arranging the strain of the graphene in special ways, the properties of the material create a huge magnetic field that was actually some of the papers were first predicted theoretically by Bonilla and co-workers, and it was measured some time ago in California, that the Landau levels of the graphene were as if there was a huge magnetic field of the order of 20 teslas or more, or 200 inside the material. It's the strongest known material, so the Young modulus is over 1 terapascal. So what I cite are experiments. Then it's impermeable to fluids and gases. So it's the thinnest known balloon, just one monolayer. And in fact, there are a lot of surprises. Okay, this one is not so old. Was early 2012. The same group by Gaim discovered that, surprisingly enough, the helium molecules of a gas were kept inside a membrane made out of graphene, but water flew out as if it wasn't. So, of course, the journalists got a good application for that. So or maybe they showed in the laboratory something, so you could this work at room temperature. So there is a paper in Science discussing these things. Someone is interested to see the science behind it. So with that, I'm going to center in what I'm interested in, which are these extraordinary mechanical properties of the material. So you can image the atoms in graphene by doing the following. Okay, so you take one monolayer of this graphene, which in the early work was done by mechanical procedures like exfoliation of graphite. Then you put it in a carbon sheet with round holes, which are about 1 micron diameter. And this is images with different resolution. So this says here. So these are the holes. So now what you do is you put here your membrane. This is the one monolayer. This is bilayer or something. Then you use the transmission electron microscope to irradiate the borders strongly enough so that you create some impurities, and this thing pin down the graphene monolayer, because otherwise it crumbles and you don't see anything. So think of this as just as a drum. When you have a drum, you have to take the borders and pin them with some wire or something. So this is equivalent of that. It's just a single layer membrane that is pinned about these holes. And then you use a transmission electron microscope, which means you are shining electrons. Of course, this is something of a, it's not totally non-destructive testing, because this irradiation may change things, as we will see in a moment. So these are like 1 micron. Now the resolution of the beam is about 1 nanometer. So when you look into this, you are able, with a high-resolution transmission electron microscope, to see essentially the atomic arrangement of the layer. Now, one thing that you see is these things. The electrons are, or the microscope is calibrated at about 80 kilovolts, which means that if you have a pristine graphene layer, you cannot knock off atoms out of that because it's low energy. However, if there are defects or whatever impurities there, these electrons may knock atoms off around the hole, because the energy for that is lower, or it can change or rotate bonds, and that creates defects. So this is part of what I'm going to talk about. Now, the other thing that people discovered immediately was that there are ripples in the graphene. So this is the reciprocal lattice vectors. If this is a plane, this would be perfect lines perpendicular to that. What they saw were diffraction spots that if you tilt the microscope, okay, you see that they stay more or less where they are. That's a sign that it's a monolayer, otherwise you'll see other things. And if you tilt it, you'll see that the spots become wider. And that is because what you are seeing is the average of these things. So if there are ripples, the normals to the planes move a little bit. And when you tilt it, you see smaller spots here, but if you tilt it, you see these things. And that those spots are bigger, and that's a sign that the sheet is rippled. Actually, the ripples I'm going to talk about are randomly oriented. They have a very small height, like below the nanometer, and wavelength varies from 10 to 25 nanometers. There are other ripples you can create by just taking a big graphene sheet and just microns long and just pulling it, like when you have a plastic and you pull it, you see that there are wrinkles that get formed. So those are also seen, but they are explained just by mechanical properties, just like when you have the sheet of plastic. So the ones I'm going to talk about are much smaller size, and their origin is not so clear as the big ones.
How big can you make the sheet up to now?
Oh, I have not kept track of the record, but apparently you can already go millimeters or something. The wrinkle experiments were just microns long. Those are enough to see it. And these ones, as I showed, they are just, these circles are 1 micron diameter. Much smaller ones. Nevertheless, in 1 micron you have a huge number of atoms. Okay, so this is an image of the microscope. So these white things, of course, are the carbon atoms. This is taken from the first paper I know about defects in graphene, which is this by Janet Meyer and co-workers in 2008. And that's how we started becoming interested in this thing. This is just a honeycomb lattice. You can think about it as a two-atom as a hexagonal lattice with a two-atom basis. So all the atoms are the same, but you can get all the dark blue atoms by just starting in one and using two of these three primitive directions. So if you do that, and you move on this side, you generate this. You move in this direction, you generate all the others. And then with just two atoms, on that basis, you generate the whole graphene lattice. Okay, so this is the same work. What they did in this work is they were just irradiating at 80 kilovolts, and then every now and then these electrons knock some atoms, switch a bond, and then instead of having hexagons all over the place, you may have this defect, which is called Stonewall's defect, because Stonewall studied the rotation first. And so you get two heptagons here and two pentagons there. And the microscope takes data every 1 or 2 seconds. So the difference between these view graphs are a few seconds, I believe 4 seconds or something like that. It turns out that this defect disappears after 4 seconds in those experiments. This is another one. You see the resolution here is not so great, so they needed some software to superimpose a lattice here and discover what kind of defect it is. So this is another defect. There is a carbon atom missing. And what you get is a pentagon and a nonagon defect. Of course, this one also disappears after a while, but not because the bonds rotate again back and you get the pristine lattice, but because there are absorbed carbon atoms, and one of them falls into the vacancy, fills it, and that's it. Anyway, the time scale for all of these changes is extremely long, the order of seconds. The first works. Okay, so this is an illustration about how this bond rotation goes. So you have the atoms, which are the things that move, and these things are just put here, just on the shortest distance between atoms. So you see that out of the pristine lattice, you rotate the bond, and you create the two heptagons and the two pentagons. The Stonewall defect. These other things are movies here. So just to illustrate how these things look without the software. So there is a vacancy, there are two atoms missing, and that in the lattice it is like two pentagons around an octagon. And okay, it's a movie of a hole created here, and if you look into this with care, you'll see some of the defects running around. Okay, so let me just say something. If you look at this view graph carefully, and you start at some point, move around in a circle and go back, you discover that you get the same number of bonds from the beginning to the end as if no defect were there. So that thing tells you that what is going on here is related to dislocations. So it would mean that the Burgess vector around this defect is 0. Now, and that's one important thing that we use to our theories. So here, I'm just reminding you what a dislocation in two-dimensional elasticity is. So this is an edge dislocation, which means that you have an extra half row of atoms here with respect to the rest. And this is the core of the dislocation, it's about this point. If you look at this, and this is what I meant before, if you start here, move around on a closed polygon and go back there, now you try to do the same in the pristine lattice, and you discover that there is one missing vector there. So you don't close the circle, counting exactly the same number of lattice lattice vectors from here to there. Now, the vector that joins these two ends is the Burgess vector, and that field marks the direction in which it is easy to move the dislocation. If you push here, you shear the sample, so here you send, you put a force that points to the positive x and here negative x. What happens is this thing. So you see that the very small motion of the atoms here, you perceive that as a motion of the whole dislocation. So this one is going to move, and so that means that the dislocation that started there is already there. And that's how the dislocations move. So a very small motion of different atoms gives you a large displacement of the defect. Okay, it is easy to see this in the easy to see that in the square lattice. In the honeycomb one, it's the same. One dislocation in this case is one pentagon and one heptagon. If you move this atom a little bit, you can perceive that as a motion of the dislocation, same as before. So here you have these two atoms are the ones that are going to move. You have a pentagon here and a heptagon there. Now these two are going to move, and you'll perceive that as the motion of the dislocation. So you see this a small motion of that means the pentagons have shifted one lattice vector, the heptagon 2, and so on. Okay.
This is a motion dictated by some intrinsic dynamics, or just a cartoon?
Okay, I'll explain a little bit how the dynamics is. This is a simulation that we did with a kind of dynamics of damped discrete elasticity. And so what we are doing is solving some model of the dynamics and imposing a boundary condition that means that you have a force pointing there on the top and another one the opposite at the bottom. Sometimes when you have several defects, the interaction between them is able to move them around. Okay, this is externally driven motion, but internally driven one with groups of defects is also possible. Okay, so this is, for instance, what happens when you have several dislocations. And here we do not apply any external force. These two dislocations see each other and they exert a certain force. Since they have exactly the same Burgess vector along the x-axis, but this one points to the right, this one so points to the left, and they experience an attractive force between them. So in this case, you run the dynamics and you end up with this dipole there. Instead of having parallel lines, they share exactly the same line, while they attract each other, glide towards them, and leave the lattice undisturbed. This is also what happened in the case of the graphene lattice. So this is the 5775 defect, so two heptagons sharing one side, two pentagons. This one is equivalent to the dipole with the two dislocations that have opposite Burgess vector but share the same glide line. So you apply this model, this elasticity model, then this thing has strength to an E length, and this is what happened in the experiment. Whereas if you just shift the glide lines so they are parallel but not the same, then you get a stable defect, which is in this case two pentagons sharing one side and the two heptagons above. Okay, so this is what the experimentalists see. Okay, this low voltage electron microscope disturbs the graphene sheet so that you rotate bonds, create this stone waste defect that are destroyed. We interpret that as, okay, they should be destroyed because they just share the same gliding line. the lattice is really disturbed all the time because you are irradiating the sheet. So that means that the electrons are transmitting some energy to the atoms, and sometimes this is enough to overcome energy barriers that keep them from moving, and that is what plays the same role as these external forces that I put in the simulations. The vacancies are disappear filled by atoms. You can actually in the experimental papers you can see a lot of different dipole groupings, like several pentagons and heptagons, and they evolve to whatever there are. So it is interesting to have a theory that predicts which defects are stable and how they are going to evolve. Now, you can do that with ab initio calculations, but we wanted to understand them from simpler models. So, yes?
Where are the atoms coming from?
Oh, the thing is different. So there are a bunch of carbon atoms.
So is the electron microscope able to see them? Because it looked quite clean. So you see that there are things moving around too fast to be seen, or what is it?
No, you can see that there are, when they ping them, you create a lot of impurities and things like that. So now one thing that you see when you study dislocations in elasticity is that they are line singularities in 3D or point singularities. So the strain and the stresses are singular exactly at the dislocation point. Of course, on a lattice, these things do not happen because you have discretized everything on it. So that was what we wanted. We wanted to modify elasticity minimally so that we would avoid the singularities and give them back the symmetry that you lose when you go from atomic lattice to elasticity. And then this thing that we modified should allow the defects to glide. Okay, so this is what we did. We discretized the 2D isotropic linear elasticity on a honeycomb lattice. So we just replaced the derivatives by appropriate finite differences on the primitive directions of the lattice. Then when a dislocation glides, we avoid having to keep track of which atom is neighbor to which one by just replacing the gradient of the displacement by periodic functions that are periodic along the primitive directions. And we used just classical dynamics with damping and fitted the time constant to the experimentally measured evolution of the defects. Now the boundary and the initial conditions that we use are given by the known solutions of classical elasticity. So you have some functions, you use them to put the atoms on the lattice and use the same thing as boundary conditions. And now, since it's all linear elasticity, you can put as many of these dislocations as you want and see how they evolve. Okay? So that's the theory that we did in these papers. And we found a bunch of results. So for instance, if you have only one dislocation, so you run the thing, and you discover that depending on where the dislocation point is placed, you see two stable defects, which are pentagon-heptagon pair or an octagon with a dangling defect. Of course, these ones are not observed because the dangling defect gets saturated with something else, and they get kicked. Then stable dipoles, depending again on how far you put the two dislocation points, can give you a symmetric vacancy or pentagon, heptagon, pentagon defect, or this other defect I showed before. Then the stone waves are unstable, and then there are more complicated defects that we analyze because they were observed by the experimentalists. This is some of the simulations with stone waves defect. So we took here two pentagon-heptagon pairs, and we did not apply any external force and release them. And what happens is that, as I said before, they attract each other, and okay, so they move around, and if you wait long enough, they reproduce, they become the stone waves defect, and then immediately they disappear. Okay? So this is an example of two dislocations with opposite Fourier vectors, but sharing the same glide line. Here we already have the same stone waves defect that has been created by radiation or whatever, and then we apply a huge shear. So a huge shear force. Here we push that way, there that way. And now what happens is that they move apart. So this defect glides to the right, this one to the left. They tend to be separated. Okay, so this is some experiment that was done later on with reduced graphene oxide, which is you start from graphene oxide and then reduce it. You take away the oxygen, and that thing is known to produce a lot of residual stress inside the sample. It gets a lot of defects and residual stress. So here you create a stone waves defect inside a region where there is a huge strain. And so what happens is that if you wait a little bit, the two defects come apart as in the simulation I showed, but of course by natural process. These are experiments that were done with vacancies. This is a hexagonal boron nitride. So here it's still a honeycomb lattice. But one sublattice has the boron atoms, the other one the nitrogen atoms. So it's not exactly as the graphene one. This one produces this symmetric processes. This is graphene, so you see these asymmetric ones. Of course, these are snapshots. Okay. Now, all of this was done with a high-resolution electron microscope that corrected, was aberration corrected, and then later people use a monochromator, so they send a monoenergetic beam of electrons, which was not the case of the previous ones, and they got a lot more resolution out of it. So these pictures were taken at Oxford. And they show these are two dislocations, so two pentagon heptagons. The Burgers vector is directed on this line. So this is one example in which, okay, so here you have the cleaner interpretation. These are the data. So here the pentagon heptagon moves along the glide line one step. So this is glide motion. And now here, after a few seconds, this one moves in the perpendicular direction. So what happens here is that the electron beam has knocked off two atoms, and then this allows the dislocations to go against the Burgers vector in something that is called a climb. So these are climb motion. So in this work, they were able to report more carefully gliding and climb motion of the atoms in the graphene. So this is something that we did with our discrete model. So you have separated these these two pentagon, heptagon defects. Of course, we put the bullet vector in the x direction because we wanted to use the known solution of elasticity, which is simpler. Now these two rotate and they move like this. And now if we artificially knock off these two and run the model, we see a climb motion. These ones, instead of moving in the x direction, they move in the y direction. So this is what was going on in that experiment. And the other thing that was interesting of the Oxford work is that they were able to, out of this picture, to take the strain and rotation fields of the dislocation for the first time. Now, what they do, they use a technique called geometric phase analysis, which they take the lattice, do a Fourier transform, so you go to the reciprocal space, then you see this diffraction spot that mark the vectors or the primitive direction in the reciprocal lattice. Now you take one of them and put a Gaussian mask on top of it. Turns out that the phase of that gives you the displacement vector projected on the corresponding primitive direction. Now you do that with vectors corresponding to the basis of the primitive of the lattice. You can reconstruct the out of the information of the phase of the Fourier transform the displacement vector. Then you take derivatives and you get the strain along the x-x direction, along the xy, and along the yy, and you also see this rotation maps. So this rotation is just the antisymmetric part of the gradient of the displacement vector. Now, this is remarkable because, as I show, this is totally different from what the predictions of linear elasticity would tell you. So this was one of the things we wanted to understand, and that's a part that is in collaboration with the experimentalist. It's another experimental view graph. So this is the one we used. Sorry. So these are a group of defects, and then there is a dipole here. So this is just 2, 5, 7 defects, one directed to the, say to the left, the other to the right. Now, we took the defect that is farthest from this piece of defects and some junk that there is there, and calculating from the experimental data the strain and the rotation field, so I'll show you first what happened. This is the experimental data. This is the predictions of linear elasticity. So you see that they are qualitatively quite different. And this is what we did with something that I'll show you in a minute. Okay. Of course. So here we have the strain energy. This would be the planar linear elasticity. These two are the two Lamé coefficients. This is the shear modulus. This is just notation. I call the gradient of displacement beta. The strain, as we know, is the symmetric part of this tensor. And the antisymmetric part is the rotation. Now, if you complement the linear elasticity with something that is quadratic with rotation with a new material constant, and calculate for one dislocation what is the elastic field, this is how we got our results. Okay. So here, so I of course do not give you all the details, which are kind of bothersome. So this epsilon is the result of linear elasticity for the one dislocation directed on about the x-axis. It gives you a rotation too, in classical elasticity. And this difference is the effect of the rotation energy. So you see that this is just as important as that. Okay. So what we found here is just that if we put the rotation modulus to be 90% of the shear modulus, you essentially map correctly the experimental data. Whereas without the rotation, you get classical elasticity, which is qualitatively different. This is just a comparison of, you just trace a circle about the dislocation of a certain radius. Here is 0.5 nanometers, I believe. And then you plot the different components of the strain and the rotation. So the red points are the experimental data. They are wiggly because, as you know, they are taken with points. So there are discreteness effects in this. And this is the formulas that we fitted. So we have a range of that material parameter gamma, which gives you a reasonable fit. Okay, so this is the other part that we did about the ripples. This is experimental evidence for the ripples. They are done similarly, so you Fourier transform these things. Now you treat the image so that the atoms that are supposed to be above the horizontal sheet are orange, and the ones below are blue. And then with that you get an idea about how the ripples are, how they are oriented, and what is the more or less wavelength. Of course, there may be ripples on top of the defects on top of the ripples, and this is some schematic diagram.
So, sorry, 5 nanometers is the height of the ripple?
No, the wavelength. Sorry, the height of the ripple is 1 nanometer or less, so they're very small in height.
Are they static or are they fluctuating?
Well, that's to be argued. Okay, so you would think that they are static out of looking at the microscope. Of course, you know, in a photograph the atoms are vibrating, but you don't see that. You don't see the photograph move unless there is some motion on the same time scale as the time takes to take that data, right? So you could say that they are static because in the times you take data here, which is 1 second or 2 seconds or something, whatever motion the atoms are doing is much, much faster, so that you average the power. But you can always argue that that's not the case. So. But the first papers that consider ripples did a Monte Carlo calculations with not so many atoms, and so this was Annalisa Fasolino, Katz Nelson, and so on, and they found that okay, the average height should be something scale like the length of the sample with this exponent, and the variance is proportional to the temperature. More or less, using molecular dynamics, this other group got the same results. And now, what is the origin of these ripples that you see? There are a bunch of theories. For instance, most of the quantum theories include electron-phonon coupling in different ways. And for instance, this paper by Pablo San Jose and Guinea and so on, they argue that the ripples come because at 0 Kelvin, with this the special variety of coupling that they use, you can show that there is a quantum phase transition according to which the bending modulus goes to 0. So if the bending modulus goes to 0, then the sheet cannot be kept in a planar configuration to get the ripples. All this explanation are kind of equilibrium explanations. We wanted to see whether we understood something about the dynamics. So this is something we tried. We are not totally satisfied with it at all. But what we did, we took just the energy of a membrane. So this is the linear elasticity part on the plane of the membrane. Here you have the bending contribution. So this is suspended, and you have you can buckle the membrane on the vertical direction, not only the horizontal. So this is the buckling part. W is the vertical component. The gradient of the displacement essentially contains a nonlinear part in the vertical direction. And now we thought that, okay, so we are going to put some force that tries to bend the sheet. And the easiest thing that we thought was we just put an icing spin so that when it is up, the atoms feel pulled from the planar direction upward. And when it is down, this force tries to pull them down. Now you just think that all of these spins are in contact with a thermal bath and flip them stochastically according to Blauer dynamics and see what happens. Okay? So that was our idea. Of course, if you play with time scales, okay, so with this we got the ripples. To try to understand them, we just did this much simpler model, which is just a bunch of harmonic oscillators in which each node feels this force due to the spins. Okay, this is the Glauber dynamics. And then we saw that there is a phase transition here in which there is a critical temperature above which the planar configuration is stable and below which the sheet buckles, okay, either upwards or downwards. If you have that the frequency of the flipping is much smaller than the acoustic frequencies, it turns out that the average over the acoustic period gives you ripples that live for a long time. Okay? So this was more or less our explanation. I think I'll skip the statistical mechanics things. If you eliminate the oscillators, essentially you get an IC model with ferromagnetic coupling, but which is long range, because that's the inverse of the tridiagonal diffusion matrix. And that thing is responsible for the phase transition. So if you start with, for instance, this is a random initial configuration. These red curve are the instantaneous vibrations, and the blue one is just the average over one period of vibration. So you see that, of course, we didn't wait for a long enough time, but you see that these things create ripples if you start with a random configuration. Here is the same, but with a regular one. So our argument is that in a long exposition time, you'll see the blue things that are. If you do the graphene sheet, then you see the ripples as they should be. You can see the defects if you put them, how they insert on the. And this is the evolution. Okay, so we start with a random distribution of these spins, and over a long time, they create a longer ripples with a longer wavelength. It's correlated with the with the length of the sample. Okay, so we also did, this model has, among many other defects, the defect that is all invented. We do not know what is the coupling constant between these invented spins and the atoms or anything like that. So we look for a different set of experiments to see whether we would be able to calibrate these parameters with experiments. We found that there are many experiments with graphene resonators in which you just take two contacts, put a graphene sheet between them, and use electrical means to excite the vibrations. These resonators are used to weigh molecules, for instance. When a molecule comes down on top of this, you see a shift in the frequency, and just analyzing that, you can figure out what is the weight of the molecule, and oftentimes for biomolecules, what kind of molecules it is. Okay? Now, the important thing for us, and this is a long story, is that this group of Adrian Bachholz in Barcelona used to interpret their measurements just a Duffy oscillator. Okay? And if you take the model we had before, and so this is the same model I had, except that I have replaced the interaction with the spins by just a double well potential. Okay? So there are many other ways to do it, but that's the one we used. Now, if you look at what is the evolution of the fundamental mode of that, then it turns out it's essentially a Duffy oscillator if you add damping appropriately. Of course, once you have that, you should, if you have damping, you should have also a noise, according to the fluctuation dissipation theorem, which should also be taken into account. So with this kind of model, we were able to fit all the parameters with the measured data in the Duffy equation, except that we had one free parameter, which is the depth of the well, for instance. Okay. So modulus that parameter, you get ripples, this is central part, and situation similar to the one I showed before. More about ripples, this is another experiment, this time in Harvard, with a graphene bilayer. So these were, instead of a monolayer, there were two layers. And they observe ripples which are the size of angstroms. So here you have a side view. So one of the sublattices of atoms is up and the other down. There are some explanations about how you could trick the Ising model on a honeycomb lattice to do that. So for instance, these people just use Ising model with next neighbors, an antiferromagnetic next neighbor interaction. And this one only, since it is antiferromagnetic, would try to do this. So the next neighbors always belong to the different sublattice. So you put one of them up, the other down, that minimizes the energy. However, if you put another antiferromagnetic interaction in which the atoms of the same sublattice see each other, then this thing creates different phases that are analyzed in the paper. So you can read a glass or things like that. Of course, what is the relation between the Ising model and the elasticity of the membrane? That was not analyzed by these people, and it is kind of open. So it's maybe another interesting thing to explore. Okay. All right. So this is more or less what I wanted to show. I have shown that the defects in graphene are the cause of dislocations. You can analyze them with these mesoscopic models. Of course, we have not put the effects of the microscope into that, but presumably this one you could do ad hoc. this is the new part in what we are doing recently. We can explain the strain and rotation fields about dislocation by just adding to simple elasticity the rotation of the rotation energy of appropriate size. And then the ripples we just studied with different hard and soft spin models coupled to elasticity. Thank you.
Okay, thank you for your talk. So, as you know, first question for students.
Do first.
There
are.
Let's begin with the first one. Questions? So, I guess,
Explain how the spin interactions can create ripples. What is the other way around? What effect does the ripples have on the electronic properties of the graphene, for example, on transport or band structure?
Well, that is something we have not investigated. We just are looking at the mechanical properties.
But is there any ideas to consider whether the ripples are a problem for the application or whether they might even be utilized?
Well, these ones are small enough. Of course, you have this strain engineering, which just by creating strains that are presumably bigger than anything the ripples can do, you can create these gauge fields, and those have a sizable effect. So probably along those lines is more interesting.
I don't understand the meaning of this rotation modulus you have to introduce. Is it to the angles between the bonds, or what is, which kind of energy or deformation is involved in this?
So this is something that is not in the linear elasticity, because so the rotation is just if you look at it, the rotation is the antisymmetric part of the gradient to the displacement. Okay. Now that is in linear elasticity, you only use the symmetric part of the gradient to the displacement, because the strains are always the symmetric part. And you have a relation between the stress and these strains. So even if you have a rotation, since it produces no energy, linear elasticity doesn't care about that. Now, it turns out that the minute you have a dislocation, even in classical elasticity, you are inducing a rotation, and you can calculate it. Not only that, the rotation is infinite at the center of the dislocation. Now, okay, all of that is very nice, but if you think of a real crystal, it's hard to believe that you are going to have an infinite rotation in a given point, and that rotating the crystal costs no energy. You know, I'm not talking about a rigid rotation of the whole crystal. Nothing well known doesn't cost anything. But a relative rotation, which is bigger near a point and smaller far apart, that physically speaking, it's hard to believe that you do not have any energy cost. Now, if you want to include that cost, the easiest, the simplest way to do it is to think, okay, in the same way as elasticity considers the square of these strains, I'll put the square of the rotation. So that's the origin about why we put this. And it turns out that is what agrees with the experiment.
You don't know the classical elastic systems in which this rotation is...
No, because, okay, wait a minute, I take it back. If you have a liquid crystal or something like that, then these directors, as you probably know, cause the stress tensor to be antisymmetric. The symmetry of the stress tensor is just a question of balance of angular momentum. So if you have another source of angular momentum like that, then typically you get this antisymmetric stress, and then you get some cost to the rotation. But in classical elasticity, when you average, you use this balance of angular momentum and get rid of the rotation. course, these are crystals, so you should not average away structure.
I think you consider suspended graphene.
Yes.
Do you think, or do you expect ripples are also important if graphene is deposited on top of another material? I mean, not suspended, but on
No, they are,
substrate.
it just follows the substrate. So the ripples, you can take them away or something, depending on how you do it. So this thing is important in suspended graphene because there the ripples are having an intrinsic life and they are not following the substrate.
And also, does it matter the way this graphene sheet is pinned at the borders of this hole? I mean,
Well, the holes are big enough so that the ripples are minute in comparison. So it's believed that they are an intrinsic effect and they do not care that much about what happens so far from them. You need to pin them because, as I said, the graphene will crumple immediately and try to form just a ball or something.
As a more technical point, when you compare with experimental results and plastic, the plastic elasticity, I mean, you have these pictures, and it seems that for the elastic, I mean, you have like, I mean, you always have dipoles.
Yeah.
Maybe you can show this picture that both experiment and your results, they show dipoles only, right? So these
No,
ones,
no,
they look like quadruples?
No, this is this is, we took away the other dislocation. So this is a there is a dipole, but the other one is not shown. So for instance, you see the difference between these. These are the effects of the other dislocation and a group of dislocations that are far apart. So this is half the picture. We didn't show the other one. The way these defects are created by irradiation, you start with a pristine lattice, and what you create has to have an overall Burgers vector equal to 0. So this is why you create these dipoles naturally.
Okay, so if no?
Is there an external parameter to control these ripples? I mean, you can increase the temperature and increase the density of them or the height of them.
Yeah, the temperature is quite important. Here, of course, we always took room temperature. But for instance, one way to control, not the ripples, but the wrinkles, the big ones, is you just take a graphene sheet like in the resonator, so you clamp it on two sides, and then you play with temperature. Now, it turns out that this expansion coefficient of water is negative, so the dilatation of the underground material where the graphene is pinned is different from the graphene itself. And then you are just inducing stresses into this, and that can create the ripples, or depending on how you do it, it can eliminate these wrinkles. So these are well-known experiments that does that. I think it was done probably 2009 or something like that by a different group of people.
Okay, there are no more questions. So, Professor, thank you once again.